Hello, and in this section we want to actually use some numbers to analyse exactly what happens with the rate constant in a first order reaction. So let's dive straight in. So take a look at this as a worked example. What you can see is a question here where they're talking about three chemicals, A, B and C. And they're giving you some proportionality information. They're saying by what proportion has the rate changed when the concentration has changed. So to start with, it talks about chemical A. Doubling the concentration of A doubles the rate of reaction. And changing the concentration of B has no effect at all. And halving the concentration of C has the effect of halving the rate of reaction. So the very first step is establishing what are the orders with respect to A, B and C. So if the rate doubles when the concentration doubles, then these have got to be directly proportional. With B, it seems like it's got no proportionality at all, and with C, if it's halving the concentration and halving the rate, then that also must be directly proportional. So I would say here that the orders are that it's first order with A, zero order with B, and first order with C. Now that means if there's three of these things in here, what the overall order would be 1 plus 0 plus 1. So I think the overall order of this reaction would be 2. The rate equation? Well, the rate would be equal to the proportionality constant K multiplied by the concentration of A to the 1, multiplied by B to the 0, multiplied by C to the 1, which would be the same as K times A times C. And here are the solutions. My head is slightly in the way of some of them, but you can see there the rate equation is rate is equal to K times the concentration of A times the concentration of C is what's obscured by my head. Now, because this is a second order reaction, the units come out as decimeters cubed per mole per second. Have a look at this question here. So it's simpler in that there are just two reactants, A and B, reacting together. And it wants to know what the rate equation is, the value of the rate constant K and its unit. So let's have a look at the information as it's been presented to us. There's three different experiments, and what they've changed each time is the concentrations of A and B, and then looked at how the initial rate has changed. Now what we must figure out is the dependency on the changing concentration that the rate has. So let's look at experiment 1 and compare it to experiment 2. You can see that the concentration of B has stayed the same, but the concentration of A has doubled. So what effect has that had on the initial rate? Well, what you can actually see there, that the initial rate has quadrupled. That if we look at 5.4 times 10 to the minus 4 and times that by 4, that would give us 2.16 times 10 to the minus 3. So that gives us a clue that A must be second order. If you're doubling the concentration and you're quadrupling the initial rate, then it's not directly proportional. If we have a look at the difference between experiment 2 and 3, you can see that the concentration of B has gone up by 1.5 times compared to A, which has stayed constant. And what you can see is that 3.24 times 10 to the minus 3 is 1.5 times 2.16 times 10 to the minus 3. So therefore, I think that the rate equation for B would basically be, or the order of the reaction with B would have to be first order. So let's take a look at our solutions here. So as we saw, when A doubled, the rate went up by 4, which means it basically has to be second order. And when b increased by 1.5, the rate went up by 1.5, which means it must be first order. And so therefore, the rate equation would be equal to the rate equal to k, the concentration of A squared multiplied by the concentration of B to the power 1. Now what we can do is we can take any sets of these values to determine the value of k. So look on any row in this table. We just need to take the initial rate and divide it by the concentration of A squared multiplied by the concentration of B to the power of 1. And so what you can see I've taken that first line, that first experiment. I've taken the initial rate of 5.4 times 10 to the minus 4, divided by the concentration of A, which was 0.01 squared, and multiplied that by the concentration of B, 0.2. And there you can see I've managed to get to an answer of 27, and there is the unit. So let's take a look now at how these different orders of reactions look on graphs. So on the top graph here, this is the concentration of X and what happens to it over time, and it comes down because it is being used up in the reaction. But that's not to say that the reaction is dependent on the concentration. Yes, the concentration is going down, but is this having an actual effect on the rate? You can see from this second graph here that the rate is actually constant. Now you can actually see that the rate, of course, would be equal to the gradient of the concentration time graph. If that is a straight line, then the rate is going to be of fixed value, which means it's zero order. There was no dependence on the concentration. So let's look at a first order graph. You can see as the concentration comes down that it's not coming down in a linear way. It starts very rapidly and then becomes much more gradual as time goes on. Now, since the gradient of a concentration time graph will give you the rate at which the reaction is occurring, if the gradient is changing, then what must be occurring is that the rate of reaction is changing. It must be dependent upon the concentration, which is itself lowering. So if we have a look at this, what we can see is that the rate is low when the concentration is low, and the rate is high when the concentration is high. Initially, the concentration is high, so the rate is high, which means it is very rapidly decreasing in concentration, and then more gradually as time goes on. So in a second order reaction, you can see that not only is the concentration changing, it's decreasing as the chemical is used up, the rate at which that is happening is also changing. It's dependent on concentration, but the actual rate itself is not linearly dependent on concentration. It's probably dependent on concentration squared or cubed or some such thing. And that means that the actual rate itself is not linear with concentration. It means that it very rapidly changes in the rate at which this reaction takes place. So for a first order reaction, you would expect that the concentration would decrease by the same proportion in the same time interval, and that's because the rate at which this is occurring is proportional to the concentration. And that means that it decreases quite rapidly to start with, and then less and less and less. But it also means interesting things, such as that it will halve in a given period of time, and it'll be in that same period of time again before we see it halve again. So the same proportion in the same time interval. And a way of measuring that is measuring the half-life, similar to what we do with radioisotopes in physics. But measuring the half-life here is quite simple. After how many seconds has the concentration halved? And then go and test to see, has it halved again in twice that number of seconds? That's the easiest way of determining what the half-life is for a given concentration time graph. Now, I've left this next section in for those of you that are so curious about this that you have to know where things come from. But this is actually a little bit tricky to understand, and if this seems to be a little bit hard, you can skip forward 2 slides and you can use the result without necessarily knowing where this has come from. But if you're staying with me, then let's take a little look at how we can relate the half-life to the rate constant. So we start off with this slightly scary formula, but it's not really that scary. It just talks about how the concentration at a particular time, which is like in brackets x, in curly brackets t, relates to the original concentration of x. That's x subscript 0. And the way we do that is we multiply it just by how many times it has halved. So if it's halved once, then what we would find is that the new concentration should be half the original. If it's halved twice, so that's half to the power of 2, it's halved, and then halved again, then it's going to be quarter of the original. If it's halved to the power of 3, it's going to be half times a half times a half, it's going to be 1/8 of the original. So that's how that formula at the top there works. So n just represents how many half-lives have gone by. That's just the ratio of what time it is now compared to what one half-life is in seconds. And for example, if it is 2 hours now and the half-life was half an hour, 0.5 hours, and 2 divided by 0.5 means 4, which is that 4 half-lives have passed. So we can actually substitute the t divided by t1/2, the symbol for half-life, into where n was in this original formula. So here's a quite complicated step. Now that we've substituted in t over t1/2 into where the n was, let's now turn our attention to the big half that's right in the middle of this formula. And we're going to use a property of natural logs that e to the power of ln anything is the same as anything, that a half is equal to e to the ln of a half, because e and ln undo each other. The natural log of e is itself. So if that's the case, then it now enables us to look at ln of a half and see what that is equal to. By the law of logs, ln of one thing divided by another thing is the same as ln of 1 minus ln of the other, the natural log of 1 minus the natural log of 2. Now, the natural log of 1 is equal to 0, which means that ln of a half is equal to minus ln of 2. Now we can substitute that into the middle of our formula. So we've got one substitution into the middle, that ln of a half is equal to minus ln2. And that means that in the middle of our formula, we're going to have e to the minus ln2, all to the power of what n was equal to, which was t over t1/2. Now, when we sort out all those indices, it means that the concentration of x at time t is equal to the original concentration multiplied by e to the power of minus ln2 over the half-life multiplied by whatever time it is right now. You might be asking, why would we want to do this? Because if we look at that minus ln2 over t1/2, the factor by which t is multiplied by before it is put in this formula, that is the part of the expression that describes how rapidly the concentration is decreasing. And that basically means if it's describing how rapidly it's decreasing, it's describing the rate. And so therefore, this ln2 over t1/2 is actually equal to the rate constant, which is what we've been working out at the front of all of our rate equations. And that we can, if we know the half-life, very easily work out what the rate constant might be. It's just ln2, a number equal to 0.693, divided by the half-life. So looking back at our example of the sulfuryl chloride, we had a rapidly decreasing concentration. We worked out that the half-life was 2,279 seconds, which means by doing ln2 of 0.693 divided by 2,279, we actually work out that the rate constant was 3.031 times 10 to the minus 4 seconds to the minus 1. And this is a much more accurate way of working out k than from the initial rate. Here are some questions. It's basically asking you to plot your own concentration time graph, to calculate manually the half-life and therefore calculate the rate constant. Now, I think what is really interesting is the fact that if you put that data into Desmos and you tell it that it is a power series, so that basically y1 is equal to the initial concentration, which was 0.4, and multiply e to some negative coefficient times x1. That coefficient that Desmos will give you back is actually the same value as the rate constant k. So what you can do is, once you've done this manually, add this data into Desmos and get it to give you back the value of that coefficient b, because that is telling you the rate constant of your formula, which you've already worked out. And so having these two values, one manually worked out and one worked out with the computer, you can then compare your percentage uncertainty, which is the difference between your two values, divided by the value from Desmos times 100%. How close were you? One final point of interest is, because these exponential laws, these decays, are very similar to what's used in physics, when you're looking at radioactive decay in physics, you use something called the decay constant lambda. Now that is exactly the same as the rate constant in these experiments. It has the same units, seconds to the minus 1 for a first order, and it is equal to 0.693 divided by the half-life, T1/2. So when and if you're doing both subjects, keep that in mind, that this is the same maths describing two different things.